네, 안녕하세요.
Good afternoon. I am Jeong Ik from KAIST. The theme that I'm going to cover today is small modular reactors and how SMR can contribute to decarbonizing marine industry. First of all, thank you for inviting me to this meaningful forum. And during the coffee break, I've met some people. When I was in high school, after passing the college entrance exam, I had to select one field, and my father is a professor at ship engineering, so he persuaded me to select another course of study. So that's why I studied nuclear. But again, I'm coming to this ocean forum, so I think this is my destiny. And my student, I wanted him to contribute and become a doctor in nuclear field, but he has become a researcher at Korea Maritime Institute. The reason why I'm mentioning this story is because so far the nuclear power contributed in the energy generation through conventional nuclear power plants. But SMR technology can be applied to the ocean industry, and it is quite an attractive source of power. And I think the nuclear power generation, if you look at the root of that power generation, I think it came from the ocean. So that's why I'm going to cover this theme. The title of this slide is New World. This is not the title that I coined. If all the scholars who study the history of the nuclear power all say that from 1940 to 1950, there was a project called Chicago Power Project, and this tenure is called as the New World Era. And at the time, there was a project called Chicago Pile 1, and the project is to make a power plant that is made with nuclear power. Leo Szilard and Enrico Fermi, the two scientists, invented the first ever nuclear reactor. You may think of this experiment as just another attempt that was made by two different scholars to test out the nuclear power or reactor, but it wasn't. It was backed by the U.S. government. Since the start of the World War II, before the U.S. engaged in the World War II, Germany discovered the uranium nuclear fission, and they discovered the possibility of nuclear power to be used in developing nuclear weapons. So in order to know whether it can be used to make a weapon, the U.S. government wanted to test whether they can build a reactor based on nuclear power. So that was the birth of this project. And the people in charge were Leo Szilard and Enrico Fermi. Leo Szilard holds the first ever patent related to nuclear reactor, and he is a very famous physicist. And Enrico Fermi won the Nobel Prize. He is the father of neutron. They built the world's first nuclear reactor. On the left side, you can see that reactor. It's really black. We didn't have the power to condense the uranium, but in order to build the reactor, we had to control the power of neutron, and to do that, we had to use the graphite. So that's why the reactor is all black. We used natural uranium and combined it with graphite and made the reactor, the new device called reactor, and the reactor worked well. And since then, the U.S. decided to embark on a dynamite project. Compton and Conan came and reviewed the Chicago Pile project, and they were the advisor to the U.S. government. And at the time, they sent an encrypted message after the success of the reactor test, and they said the Italian navigator has landed in the new world. It is a smaller world than he believed it was. So the success of the project was just like discovering a new continent or new world. There was a message sent by Conant. And you saw the movie that was released last year, Oppenheim, right? And Robert Oppenheim led the other projects since then. I guess many of you may not know about nuclear fission and physics related to nuclear power, so I'll spend some time to explain to you. I guess you may have seen this picture before, but this needs a little bit of explanation. And many forget to cover this part, so I will. There's a neutron. When it meets with uranium-235, when it meets with the elements, then it collides, and that collision is referred to as nuclear fission, just like the cell fission. And it creates 3 different neutrons, and the entire process is called nuclear fission. It is very particular because after absorbing the neutron, it creates some heat and energy, and then again it produces another 3 different neutrons, and there's no other fission like this. Again, it produces heat and energy, and again that it creates the neutron, which can lead to the chain reaction. So this is the characteristics of the nuclear fission, and that's why the nuclear power plant is using uranium-235. It can replace this chain reaction using other elements. We may have used it, but uranium is the only source that creates the chain reaction. So uranium-235 is the only source. Natural uranium-235, in order to use it commercially, we need to tone it down to 5%. And in the next generation power plant, the usage will have to be increased by 10 to 15% or 19%. So we condense the uranium to be used in the power plant. You may think of the uranium as the feedstock, and neutron is just like the oxygen. And there's a neutron part here. Neutron exists in the nuclei of the element, but it doesn't exist in the atmosphere. So a neutron is something that we need to artificially make in order to produce energy from uranium. But producing the neutron is really difficult. So before discovering the nuclear fission of uranium-235, there was no other. People thought that there is no other way to make the neutron, so that's why we couldn't think of a way to use the nuclear power or nuclear radiation in the treatment of the medicine. So that's why it was an innovative discovery in terms of nuclear engineering. So let's say we have made neutron through an artificial way and combine it with uranium-235. Then we can get 3 other neutrons. So this is the biggest characteristics of nuclear fission. We don't have to put in another oxidant, and oxygen is not needed in this process because neutron can reproduce again and again in this chain reaction. So I've showed you the nuclear reactor. Once we make the neutron, then the population of the neutron can be increased and scaled up using the nuclear fission process, and we can artificially control this process using that nuclear reactor. And through that process, we prove that the humanity can control the neutron according to what we wish. And that's why the J.B. Conant mentioned that it's a new world. To give you more explanation about the process, the neutron that comes out of the nuclear fission process, in the slide you can see slow neutron. The slow neutron is absorbed with uranium-235, and the 2 other neutrons are produced. So there are 3 neutrons out of this fission process. and they become fast neutron. But the problem here of the fast neutron is that they are not absorbed well to uranium-235. So we need to prevent the slip of this fast neutron. So we need to convert this fast neutron into slow neutron. So we need another material to make it slow, and one of that material is graphite. And graphite is used as a moderator. The green part, all the particles that's drawn on the green part are moderator nuclei. If they collide with the neutron, they absorb the energy of the fast neutron and make it slow. So the function of the moderator is to make the neutron slow. And one of the important part of the nuclear reactor is the material such as graphite, which is moderator, and the raw material and coolant. So these three elements are important parts of nuclear reactors. So nuclear feedstock, moderator, and coolant. Depending on the need for the amount of these three elements, the scale can get big or small, and we can engineer it in a way that we wish. If you look at the development of the SMR, there are 70-some countries who are trying to develop SMR. They are coming up with different ways to design a reactor. The reason why we have different types of SMR design is because the combination of the three important elements are different according to the company's approach. But that's why the market for the SMR is uncertain, because nobody knows which reactor is going to rule the market. So let's look at the energy density of uranium. We compare it with carbon or oil. So the basis here is crude oil. Let's say the petrol oil is set to 1, and energy density of uranium is 2 million times higher than petrol oil. But uranium is the nuclear reaction that produces a lot of energy, the maximum amount of energy. And another way to get an energy is because it's through the nuclear fission. But through the nuclear fusion, we only can get 1/10 of the energy. So nuclear fission is the biggest, is the most promising way to get most amount of energy. And again, through the nuclear fission, we can get another neutron. So that's why the nuclear power plants are using nuclear fission process. I don't like the term nuclear power plant because most of the power plants, the term of the power plant or title of the power plant comes from the feedstock. But nuclear power plant, we don't use the nucleus as the feedstock. We use uranium as the feedstock, but we don't call it as uranium power plant, so I don't like the term nuclear power plant. You know that the Manhattan Project ended up with success. And after the war, the U.S. thought that Manhattan Project led to a lot of fruitful results, and they had the super gap in this science. And other countries, the U.S. thought that other countries would have difficult time in producing this same results in the nuclear development field, but other scientists got back home and they developed their nuclear power. In the 1950s, there's a man, Hyman Rickover. He set up his mind to develop nuclear propulsion vessel. He engaged in the Manhattan Project, and he had a lot of knowledge in terms of science of this field. And many people think that nuclear submarine is one of the biggest weapons that used in the 20th century, and he thought that it can be a powerful weapon. So Hyman Rickover decided to develop the nuclear-powered vessel, nuclear submarine. Other engineers who were in part of the Manhattan Project at the time mentioned that not be able to have or house the nuclear reactor. At the nuclear reactor of the nuclear submarine will be impossible. To solve that problem, Hyman Rickover gathered General Electric engineers to solve the size of the nuclear reactor issue. So at the time, scientists knew that uranium is the most powerful element that can produce a lot of energy. And engineers found out that the volume of the graphite took a lot of space. So Hyman Rickover ordered the scientists to replace graphite to some other material, but there was no other material that can replace graphite to make a reactor. And again, he pushed the engineers to come up with a new design. And one engineer suggested to change the coolant. At the time, we used water, and he suggested another material to use in the cooling process. So if we combine the moderator part and the coolant part into one, then we can save space. So Westinghouse and other engineers came up with the idea to use water as a moderator and the coolant. And GE at the time took a step further to build a reactor that doesn't need any moderator. So the design that GE came up with was to combine only the material of the feedstock part and the coolant part. That's the secret behind it, making the nuclear submarine possible. So first was the water coolant technology. And that was the first ever nuclear submarine, USS Nautilus technology. That was a game changer in the submarine weapon system. If you look at the nuclear power plant that exists nowadays, all use pressurized water reactor, PWR, that was used in USS Nautilus. So water is used to cool down and moderate the speed of the neutron. And in the PWR process, we use liquid water. And in the process, it creates steam. And steam is used again to boil the water again. So the nuclear reactor system is kept in the high pressure status, and the steam system boil the water, and that required another machinery part. The PWR system is unique because it is built in a confined space. In order to do the maintenance of the machinery, then all the part was in the steam part. So in the life cycle of the nuclear submarine, the maintenance couldn't be done in the nuclear reactor part, but all the parts that require maintenance was in the steam part. So those parts was free from nuclear radiation because the other part was in a confined space, so maintenance worker can get in and fix it without a downtime of the submarine. So PWR technology is used in the nuclear power plant of nowadays, and facility capacity is quite high, and maintenance capability is quite high for PWR as well. So PWR method was very successful. So that was developed for the submarine for the first time, and then it was used to build nuclear power plant. Demand for the nuclear power plant rose after the World War II, so that's why we started to build the nuclear power plant. And that went to the private sector, and then the private companies built a PWR nuclear power plant. And the economic profit out of PWR was quite good, so that's why the nuclear power plants were built across the United States. So commercial nuclear power plant was built first in 1950s, and more than 100 of nuclear power plants were built after that. the number rapidly increase. If you see the y-axis, it is the electrical output of one nuclear power plant, and the output increased as time went by as well. If you see the middle part of this graph, the second generation of nuclear power plant, if you compare to the first generation, the first generation tried out many attempts in the design, but in the second generation of nuclear power plant, selected one most efficient method, and they applied economy of scale to increase the profitability out of nuclear power plants. So second generation is all about increasing the profitability. And in the second generation, most of the nuclear power plant accident we knew, for example, Fukushima power plant accidents, and so we see a lot of accident coming from second generation plants because they only focus on the profitability only by increasing the scale and output of the plants. So that's why we ended up having a lot of accidents that we couldn't foresee. In the process, if you see the third generation power plants, for example, UAE plant or Czech plants, or new U.S. nuclear plants that started operation, are all third-generation nuclear power plants. They consider economic profitability and safety at the same time. So it's 10 times or 100 times safer than the second generation. So this is the trend. And now we have the SMR technology. The background of the SMR is because the world is paying a lot of attention in carbon neutrality, and new and renewable sources of energy came into the power generation chain. And renewable energy has a load fluctuations. So to complement that fluctuation, we need to have another alternative technology. There are some countries who lack the technology to handle this volatility. So that's why we came up with SMR. It can complement such volatility. There are not many countries which have big power plants like Korea. So if we think about ways to finance a nuclear power plant in a sustainable way, even for the underdeveloped country, SMR can be a solution. The reason why we scaled up the scale of the nuclear power plant is to have a better output. So in order to make it small, it gets expensive. So in order to reduce the cost, we need to modularize the equipment. So equipment needs to modularize, may be able to make it in the manufacturing line, and installing the modules will have to be easy to make this technology commercial. Another important thing is that SMR, the safety is, as mentioned, is increased by 100 times than the previous generation because it's small. Nuclear reactor is easy to cool, and the radiation that is stored in one reactor is smaller than the second generation. Let's say if there's an accident in one reactor, there's less possibility of radiation release from the reactor, and the impact is smaller than the second generation. If you see the recently certified SMR, the technology regulatory body actually released the requirement to set up a safety zone. So the biggest hurdle that we need to handle with the nuclear power plant is to persuade the public to establish the power plant near their home, because people don't like the nuclear power plant to be built near their home. So it is really difficult to set up a plant, and there is a regulatory hurdle to select the site of the power plant to be far away from densely populated area, because we need to protect the people or residents from the radiation. So that's why we have set up such regulatory requirement. But in case of SMR, if you see the U.S. regulation on new-scale plants, so even though there can be severe accidents, there is no need for residents' evacuation. It is not just the companies' reasoning behind their technology. The regulatory bodies said okay to set no safety boundary for the residents. SMR, in short, contribute to enhancing safety. As the reactor got smaller and smaller, we need many innovative technology. And one of the important things is digitalization. So previously, the nuclear power plant needed around 20 operators or so. But in case of NuScale, which is SMR plant, the plant is operated by just 3 human operators, and 20 units can be operated by 3 operators. And the maintenance workers, to reduce the people cost, it is better for us to reduce the maintenance headcount. But SMR is a good way to reduce that cost. In order to guarantee the economic feasibility of SMR, then first we need to select the right site, and second, we need to apply the digital technology to reduce the required personnel, and third, we need to have the modularized technology to bring down the cost of SMR. Then it will guarantee the commercialization of the technology. So the biggest market for SMR is coal to nuclear market. Coal-based power plant is exiting the market in a quick pace, but SMR is difficult to be applied to large-scale nuclear power plant. Let's say if you are to establish a nuclear power plant in a small area, then we need to select SMR. Coal-based fossil fuel, or when you set up a plan to establish a power plant, we need to set up wires, do wiring for transmitting such power. So instead of coal, we can think of using SMR. And I think in going forward, SMR will be able to replace the coal. And the CapEx cost is 35 to 40% lower if we use SMR, and we can also inherit the people who worked in the coal power plant to work in the SMR. So labor issue is another thing that we can solve through SMR. The Terra Power Company is leading a project in Wyoming, and they're doing a demo project for SMR on the issue whether the SMR can replace coal. The U.S. is experimenting on coal to nuclear, and other countries are preparing to do so. So this is one of the biggest markets that SMR can enter into. And another market area is using big data and AI. Then the power demand will go up, and the power generation can come from SMR, so that's another market. Recently, Microsoft requested to reoperate TMI power plant to use it in their data center. I think there's a coupling between IT field and nuclear. So that's why I think nuclear power plants will take up an important part as time goes by. So this is the categorization of each generation of nuclear power plants. So starting from generation 3 and 4, it will be the future generation. We will not use water as a coolant, and this will require innovative design. By eradicating the usage of water, then you will have to find a way to replace water, for example, solid sodium or molten sodium or gas as coolants. If so, we could be able to see the advantages that PWR didn't have. And that will lead to the birth of Generation 4 SMR, or nuclear power plants. While we saw the birth of second generation and third generation power plants on ground, there was some linkage between the ocean as well. So in the Navy, they used the nuclear submarine and developed a lot of nuclear air carrier. But in the private sector, nuclear power was also used. Russia developed nuclear propulsion system and floating nuclear power plants. got another attention. And in Russia, SMR that was really matured in technology is KT-40X, which is a floating nuclear power plant. So floating nuclear power plant is another field, and GBS, gravity-based structure, is to build the structure offshore. And most of the nuclear power plant existed in the coastal area. Then if you can make it at the yard side as a turnkey, then GBS structure is very useful in the construction of nuclear power plants. And many scholars and researchers spent some time on coming up with the method. So these were the efforts that was made by the private sector. The US, Russia, and Japan, they developed a nuclear-powered ship, but many projects failed not because of the nuclear power itself, but because of the crew member. The system itself required a lot of manpower, and then in order to hire that enough manpower, the economic feasibility dropped. So that's why they didn't use the nuclear propulsion system and instead use other conventional sources of power. Let's say if we are to develop the nuclear propulsion vessels, then we will have to minimize the use of operators and maintenance workers. If the shipping industry is to opt for nuclear power as a propulsion system, then one thing that should be solved is to minimize the headcount costs. This is a special purpose vessels. So the Navy vessels are built for special purpose, so they could use nuclear power. And in 2021, this is the article from 2021. This is Bangladesh case. Russia was building nuclear power plant in Bangladesh, and the parts had to be supplied. And they used nuclear-propelled cargo ship to transport that parts. So I think it was a very symbolic case because they transported the nuclear power plant parts through nuclear-propelled ship.
And the technology based on pressurized nuclear reactor was created in the past, but it had issues in the past. So the next generation of the nuclear reactor is molten salt reactor. So molten salt reactor has the biggest advantage, which is it needs a coolant moderator and also a nuclear reactor. And there's a SMR, which is a molten salt reactor. It does not need a moderator, and also the nuclear reactor and also the coolant can be combined as one. So the very first and also next generation nuclear reactor is this one. So it's a very simple structure, and at the same time, it's the smallest in size, which is best suited for vessels. In addition, up until now, the fuels for the nuclear reactor used to be liquid. But then the molten salt reactor, the fuel is liquid and also 300 or 400 Celsius degrees as a melting point. So whenever it is leaked, it becomes solidified. So when it is leaked, it is safe. So in terms of stability, and also in terms of the size and performance and operation of nuclear reactors, this has a huge potential as a next generation nuclear power. And there is a TerraPower, a company, and as an engine for nuclear power vessels. The concepts such as molten salt reactor can be used, and also currently there are companies like TerraPower, Southern Company, and Core Power are coming together to develop next generation nuclear reactor. And of course, the shipbuilding company is also making a huge investment. in order to develop next generation nuclear reactor and to contribute to development of the shipbuilding industry. And this is an article released about the work done by TerraPower and KSOE. And this is a nuclear reactor called the Eureka by Korea. And the physical characteristics is quite similar to the work done by the TerraPower, and we are utilizing innovative technologies just to make it best suited to vessels. And feasibility project is there, which is under the Ministry of Science and ICT, and we are saying that we are going to prove it's a concept. And we said that we are going to do it by mid-2030, which is a very ambitious goal, because it is unlike conventional reactor. Even to develop a conventional reactor, it takes us 5 to 10 years, but this is like a molten salt reactor is something very new in the history of 80s of a nuclear reactor engineering history. This is the very first one that we try to develop. So the roadmap that we have is a very ambitious one. Nonetheless, we believe that that will end with a great success utilizing current technologies. And among the SMRs, this is one of the most successful SMR, KLT-40s by the Russia. It's a floating nuclear reactor. And there's a city called Pevek. And that Pevek city received the electricity from the nuclear power plant on land, but it was closed down. So in order to receive the electricity, they had to lay out transmission network, which goes for like hundreds of kilometers. So the Russia decided that having this floating nuclear reactor would be much more beneficial for the Pevek to receive electricity. So this is a very successful one, and in terms of economic feasibility, this is the very first thing that they are doing, so that economic feasibility is not known or not proven yet. And this is a small modular reactor, ACP-100 by China. So this is going to be developed into a vessel, but at the moment the construction is underway to develop it as a reactor inland. The construction is nearly completed, it looks like. So small and pressurized modular reactor among 100 megawatt size. The China is leading, and once it is put into a vessel, then floating nuclear power plant could be built by China. And there's a Bandi 60S, which is developed by KEPCO, and that was jointly developed with the Daewoo. Later it was changed to another company, so the development is still underway for Bandi 60s, and this is how it looks on your right hand side. And the design was upgraded lately. So in Korea, we are already working on a floating nuclear reactor. And also Samsung is using molten salt reactor, working with the Seaborg on floating nuclear reactors. So this is not just simply used as an engine to power the vessel, but it could be differently used. And also in the meantime, MIT is also working with a very famous maritime company to come up with this kind of a concept. One thing that they refer to is GBS structure developed by KAIST. So GBS technologies, I think I don't have to further elaborate because you will already know this. This is like a concrete plate, and all the equipment and the parts will be put into concrete box, and we float it in the water and generate power. And the biggest advantage is that we can just fit the nuclear power plant inland into the concrete. So the operation method is the same. as it is the one for the land. So we can directly apply technologies applied inland to the ocean. And also the Korea as well is developing this technology, and in order to properly construct a nuclear reactor, which is floating, they have considered GBS technologies. So I think this technology is not visible for smart, but also SMR, all of the small size, the small modular, the reactors also can embrace these technologies. So many SMR development is underway, and we could export those to other countries. And there's a company called Thocorn, and they have used GBS technology structure, and they set the layout. And as you can see on site, they have just placed it, just like the one located inland. So this is the concept that they have proposed. So using the SMR technology and ocean technologies, so many activities are underway for the next generation nuclear reactor. So the carbon-free and also towards net zero, I think these technologies can contribute to achieving that. Of course, many regulations should be there. In order to come up with these regulations, the UK and also the US are putting a lot of thoughts into it, along with Korea and also IMO, IEA. Also thinking about how we can apply the nuclear reactor technologies onto this industry. So globally, once we successfully build a consensus, then we'll be able to use nuclear reactor energy in the ocean. And there are people even to build the yacht, which is powered by nuclear power. I think it will take some time, but within 10 to 20 years, every time, I think the nuclear powered vessel can be there in the ocean and the maritime.